The unit step function is a mathematical representation of turning on and turning off. How does this magical function work, you ask? By being a piecewise function. When t is less than 0, the unit step function is 0, or off. But when t is greater than 0, the unit step function turns on. It is 1. The unit step function can be graphed as something that is 0 and then suddenly jumps to, why did it do that? And then suddenly jumps to 1 at time equals 0. The clever bit about the unit step function is that we can multiply it by some function that we're going to turn off or turn on at time equals 0. For example, we had 5u of t, then that would be modeled as being 0 until time equals 0, and then suddenly jumping up all the way to 5. I know that's a really terrible drawing, but there it is, right at 5. And it just goes on 5 forever, because it turns on. At time equals 0, u of t becomes 1. So this is just 5 for t is greater than 0. We could also multiply the unit step function by a function such as t. When the unit step function turns on at t equals 0, t turns on, and we start seeing it happen. Observe that this purple line is 0 until 0, and then it starts going up as t. The unit step function can turn on at other times. When we want to represent a different time that the unit step function turns on, we put it in the subscript. This unit step function turns on at t equals 3. So if we had a graph, then this unit step function would turn on at t equals 3. You can add unit step functions together to turn on or off more things. For example, consider u3t and u5t added together. This says that at 3, this unit step function turns on, so it becomes 1. So we'll start drawing that. We'll write it turning on at 3. But then at 5, u5 of t also turns on. So that's another 1. So we'll go 3, 4, 5, and then boop, up to 2. So we can label this as 2 and label this as 1, and then label this as 5. When we subtract a unit step function, that represents often turning off a function. For example, at time equals 3, we turn on number 1 because u3t becomes 1 at time equals 3. But at time equals 5, we turn off 1. We subtract 1. So the way we can read this is that it's 0 until it hits 3, and then it jumps up because it's turned 1 on. And then it goes and goes and goes until it reaches 5. At 5, this unit step function turns on, but it's being subtracted. So it really turns off the number 1. So the number 1 is turned off. And it goes like this forevermore. The unit step function has some power as a tool because it can be used to represent any piecewise function. For example, consider the following piecewise function. From 0 to 3 in time, it has the function value 2t. However, from 3 to 5, it has the exact value 6. From time equals 5 to time equals 8, it has the function value negative 2t plus 16. And when t is greater than 8, it has the function value of 0. We can represent this piecewise function by reading from left to right or from top to bottom. At time equals 0, the function represents 2t. So we can write this function as being 2t. So we're rewriting f of t. So it starts as 2t. But at time equals 3, the 2t turns off. To represent that, we write minus 2t u3 of t. Observe that when t becomes 3, this becomes 1. That means that because we have the subtraction, we're basically taking away 2t from this function. So after time equals 3, we have a 2t here, but we also have a 2t here, and they cancel each other out. So at time equals 3, we can use the unit step function to turn off the function 2t. Now we also want to turn on, at time equals 3, the function 6. So we write plus 6 u3 of t, because at time equals 3, 6 starts happening. It appears. Now you may be able to tell what happens at t equals 5. At t equals 5, we turn off 6. Sorry, this should be u5t. And at t equals 5, we turn on negative 2t plus 16. So this becomes plus negative 2t plus 16 u5 of t, because that turns on at time is 5. Then at time equals 8, we turn off negative 2t plus 16 using u8t. And because for t is greater than 8, it's supposed to be 0, we're good. We've turned off everything that we ever had. And we've now expressed this piecewise function as a bunch of unit step functions. You may think this seems like a bunch of silly mathematical finagling when this is really just this expressed slightly differently. However, the Laplace transform, something you may have learned about in ordinary differential equations and will learn about again soon, is very amenable to the existence of unit step functions. Additionally, unit step functions represent switches in circuits, or the turning on and off of a power source, and this is extra convenient, because we may be able to solve the step response of a circuit using unit step functions and the Laplace transform without having to solve crazy differential equations. That said, let's talk about one more interesting thing that can occur when you try to use a function and turn on a function with a unit step. When we had t, everything was all well and good. From time equals, up until time equals 0, let me use a different color here, up until time equals 0, the function t was totally off. At time equals 0, well, t equals 0, and time equals 1, well, t equals 1. So we had the function t starting from 0 right here. But what if t turns on at a different time? What if t turns on at the time tu4 of t? Well, let's just think about that one. Until time equals 4, the function is totally off, right? So it just looks like this straight line. But at t equals 4, and when everything turns on, what is t? T is 4, so t is all the way up here. So it jumps straight up and then starts to keep going along with our original tu of t. So it's like we just restore the existence of t. And sometimes that is not what we want, especially in the Laplace transform, which tries to treat a function as starting from its beginning or its position at 0. So what are we supposed to do when we get something like t and we want to start it from 0 instead of from 4? If we want to start a function that looks like t, that looks like this, at 0, at y equals 0, but we want to do that when the unit step function turns on at 4, we need to shift the function t over to the right. And you may recall from algebra that you can shift a function to the right by shifting its independent variable input with a subtraction. So if we want to move the function t to the right by 4 units, we need to rewrite t as t minus 4. T minus 4 acts just like the function t, except that it starts at t equals 4. So if we write the unit step function t minus 4 u4t, let's see what happens. Of course, as long as t is less than 4, the unit step function is off, so it's just a plain 0. But at 4, well, let's plug in 4 here. 4 minus 4 is 0. 5 minus 4 is 1. So what we end up getting is a function that looks just like t, but it starts a little later. And this is a way to turn on a function type that you want to turn on, but shifted to the right. Maybe you want to turn on a quadratic at time equals 4, but you don't want it to start at 16, which is what would happen if you plugged in 4. You want it to start at 0. Well, we can rewrite this as t minus 4 squared, because the input t has been shifted, u4 of t. And at time equals 4, we can plug in 4 here, and we get 0 squared. So the quadratic, so we can follow it like this, starts at 0, at t equals less than 4. And then at t equals 4, boop, it starts doing its quadratic thing from the very beginning of the function. If you ever intend to perform a Laplace transform involving functions that turn on at a given time, such as time equals 4, you need to make sure that the function you have out front of u4 is in this form. It needs to be a function of t minus 4. Let me give a couple examples to explain what I mean. Suppose we have the function tu3 of t, and we want to be able to perform a Laplace transform of it. You may not be able to perform a Laplace transform of it, but the point right now is to make it into a form where this function t, which looks like this, or it looks like this, starts at 3 and not at 0. So the function starts doing its thing from its beginning of 0, but at time equals 3. Now the issue is that we can't just replace this with t minus 3 and be done with it. We need to finagle things around a little bit to produce a function which is in the form some function of t minus 3. How can we do this? Here's what we'll do. We will write t minus 3 plus 3, u3 of t. And we'll rewrite this in yet another way. We will put parentheses t minus 3 plus 3, u3t. Let me erase this real quick. Observe that this is a function of t minus 3 plus 3. What do I mean by that? Suppose f of t was equal to t plus 3, and we plugged in t minus 3. Well, f of t minus 3 would be equal to t minus 3, see we plug in t minus 3 for t, plus 3. This is a function in t minus 3 because every instance of t is really an instance of t minus 3. This is similar to the way that the following function, smiley face plus 3, is a function of smiley face. We can plug absolutely whatever we want to the smiley face. We can plug in t, we can plug in 5, we can plug in t minus 3, because we're allowed to plug in whatever we want to a function. So we can look at something that looks like it has t minus 3 in it, and we can say, every time I see a t minus 3, all I see is t minus 3's instead of just plain t's, so I could write this as a function in t minus 3. Let me give another example to explain what I mean. Suppose you have the following function, t minus 3 squared plus t. And suppose you introduce t minus 3 plus 3 to this function. So minus 3 plus 3 is just 0, so we didn't really introduce anything. But suppose I put a parentheses here. Observe that every time you see a t, you also see a t minus 3. So you could imagine this function as being either, let's call it either g of t, where if you plug in t, you plug it into this thing, or let's call the function f of t minus 3. G of t just looks like this. But f of t minus 3 is some special function that you can plug t minus 3 into to get this whole thing. And you may be able to guess what that function is. F of, let's call it smiley face, is equal to smiley face squared plus smiley face plus 3. Smiley face squared plus smiley face plus 3. So if you had the following function, t minus 3 squared plus t times u of 3t, and you wanted to make it Laplace transformable, you'd need to make it a function in terms of t minus 3, which we can do by, once again, introducing the minus 3 plus 3. Plus t minus 3 plus 3, put our parentheses, u3t. And now we have a function totally in t minus 3. Multiplied by u3t, and it is now Laplace transformable. We'll talk more about Laplace transforms and how they can be used to solve problems involving unit step functions soon. But hopefully this crash course in unit step functions and how they can be finagled and wiggled with is helpful to you both for ordinary differential equations and for our future work in Laplace transforms.